so we're ready to start. Class, sorry for the delay. There was a small delay because of the exam, and then another one because of our classical physics mechanical fault. It's a great pleasure to have Dr. Mazza with us from Scuola Normale Superiore of Pisa, visiting our group and the school and the university here for a few days. He'll be talking about quantum sciences as I asked him, in a layman's level as much as possible. Do feel free to ask questions. The talk should be accessible. This is the first part for the general audience. Leonardo has done his PhD in Max Planck Institute in Munich, in one of the maybe top 3 groups in the world in quantum sciences, and now he's a researcher at Pisa for the last 3 years. And Leonardo, to you. Thank you.
So, thank you very much. So I would like to start thanking Dimitris because it was very nice, the invitation here to Krita. I'm actually enjoying very much my time here, both in and outside the university. And okay, so as Dimitris was saying, I will speak a bit about this idea of quantum sciences, and subtitle is this idea of controlling and using complex quantum systems for doing things which basically we could not do without complex quantum systems. And right, so I was asked basically to give a talk about mainly quantum mechanics for people who don't know much, at least, about quantum mechanics. So I try to leave it really at a non-technical level, more focusing on ideas. And so please ask questions if I'm going too fast on things which are maybe not so clear. So, right, so just a bit of an outlook and overview of what I'm going to speak about. Right, so we are going to speak about quantum mechanics, and quantum mechanics, was basically developed in the beginning of the late last century, when there were experiments, more and more experiments, and more experimental evidence that atoms and things as small as atoms actually behave in a different way. So, I was writing here, physical objects of atomic dimensions display unexpected features, which unexpected at least for the physicists of that time, which could not be described with the physical models which were employed before for describing any microscopic object of, let's say, the size of this mobile telephone. So all of this endeavor, which was taking a lot of years, and there was a lot of discussion and challenges and fighting between people, between different ideas and so on, brought at the end to the development of the modern theory of quantum mechanics, which if we just have a look in Wikipedia, for example, just to see what it is, it's the science of the very small, the body of scientific principles which explains the behavior of matter and its interactions with energy on the scale of atoms and subatomic physics. So it's basically the physical theory which we have and which we use currently in everyday life to describe whatever happens at the size of an atom or even smaller, basically. So just to really try to stress, how novel and how striking, in a sense, was a quantum system. Let's try quantum physics and quantum mechanics. I would like somehow here to try to contrast it with whatever was developed before. So we have a body of theories which were developed in the centuries before, in the 17th century or 18th century, which were used, to describe the properties of what I will call macroscopic objects, objects which are of the size of ourselves, for example. So we have Newtonian mechanics, which is usually used to, well, it's what is based on this building, basically, or Maxwell's electrodynamics, or even Einstein's relativity. All of these physical theories, have been basically developed in order to describe macroscopic objects. And on the other side, we have all the quantum theories, so which are used for the description of atoms, molecules, or even nuclei, which basically all start from quantum mechanics. And we have quantum field theory, which is a way to describe even smaller things, or quantum electrodynamics, and so on and so forth. And what I really want to stress is that, in a sense, the difference between this body of theories and this body of theories is so strong that people started to develop really a new jargon and started to call all of these theories the classical physics, and all of these things the quantum physics. And it's really a bit of the difference really between something which looks like old and ancient and well-developed, like, I mean, the classical Greek sculpture, and something completely new and unexpected and completely extravagant, like quantum physics and the quantum world. And actually, this idea of classical physics contrasted with quantum physics is not my idea. It's really technical jargon. So I really want to introduce it now. So whenever I will speak about physical theories or macroscopic objects, I will often use the word classical. So, I mean, whenever I will speak about classical, I mean whatever is not quantum and it's on the side of ourselves and of our usual experience. So since, I mean, I don't expect many people here to be very familiar with the idea of quantum mechanics, it's maybe important here to try to see, so why these people were so shocked by quantum mechanics and why we started to call whatever came before like classical. And so here, I mean, I was thinking a bit about that, and I think that these are probably two of the most striking properties of quantum mechanics and two of the reasons why we really speak about a new body of theories. The first one, which is written here, is that there are measurable quantities which cannot assume a continuous range of values, but only some very well-defined discrete values. And this is the idea of the quanta, which then gave the name to the theory of quantum mechanics. So, for example, I mean, if you consider, I mean, this is something which probably you have already heard, but let's repeat it now. If you consider the sun and the earth going around it, for example, and you want to measure whatever quantity related to the motion of the earth around the sun, like, for example, the angular momentum or the velocity or the position, basically there is no physical limit to whatever value you could obtain. You could really obtain what, I mean, depending, of course, on the situation, there is no physical reason why the earth shouldn't be going at some kilometers per hour or something plus epsilon or something minus epsilon and so on. If we look at a very similar atomic situation in which we have the electron going around the nucleus, so things are completely different. So it's not possible to measure, for example, the angular momentum of the electron. It's not possible to measure whatever values. There are whatever value. There are only some well-defined values which you can measure, which can appear, and other values are just forbidden, just impossible. And this is somehow a bit of the idea of quantization of physics. And I think the other important point, which really makes quantum mechanics different from classical mechanics, is the second point here. In general, there is an insuperable limit to the precision with which the result of a measurement can be predicted. And this is what is usually known as Heisenberg's uncertainty relation. So it's not possible, for example, to imagine to be able to measure the position and the velocity of our electron going around the atom with whatever precision. So there is actually a lower bound. So you cannot be more precise than something, which is actually mathematically well stated by this Heisenberg principle. And actually, quantum mechanics at the end only outcomes the probability with which you will measure some values, not the exact value which you will at some point measure. And I think this makes it really, really different also from classical physics, because when we speak about the Earth going around the sun, there is no reason why you should you shouldn't be able to measure with good precision the position and the velocity of the Earth, for example. And somehow, having done this very fast, very small introduction about the ideas of quantum mechanics, I would like now to get to a very interesting lecture given by a very well-known physicist, who is Richard Feynman, who gave this, I would say, seminal lecture in 1959 at Caltech in California, which is called Plenty of Room at the Bottom, and which is considered to be the lecture which actually gave it a kick to all of this field of the nanoscience and nano whatever, if you want. And so I think there is a very interesting paragraph in this lecture, which I reported here, which I would like to read, which says, when we get to the very, very small world, say circuits of 7 atoms and so on, we have a lot of new things that would happen that represent completely new opportunities for design. Atoms on a small scale behave like nothing on a large scale, for they satisfy the laws of quantum mechanics. So as we go down and fiddle around with the atoms down there, we are working with different laws, and we can expect to do different things. So in 1959, quantum mechanics was already developed. It was already accepted. I mean, people were actually challenging other frontiers. And Feynman is somehow the first one which says, okay, right, we know how things work now. Can we actually use them? Can we actually do something new with these things? And this is really a change of paradigm from understanding the small world to using it, exploiting it, manipulating it. And somehow this is what still, I mean, we are trying to do. And I would say that this is what basically is my talk about. So what can actually expect to do with quantum objects with respect to other big classical objects. So here is the outline of this seminar, and it's divided in 2 parts. The first part, which is about this quantum science and the idea of actually doing something with these quantum objects, is, I would say, the most accessible, and I try to have it as the most, let's say, at the least technical level. And I will actually speak in particular about two important ideas which have been developed in the last decades, which is the idea of doing a quantum computer and the idea of doing a quantum simulator. And after that, I will try somehow to get a little bit more technical and actually get a bit more close to what I'm actually doing in my very small research in Pisa and before in Munich. So this part will be slightly more technical. The first, it's about quantum memories, which is one other application of quantum sciences. And I will speak about the idea of using topological order in these systems and also the idea of using recovery operations. So in particular, this second part will be the one which will mostly explain our ideas in Pisa and Munich. But anyway, I mean, I'll try to have everything at a very accessible and non-technical way. So, and then there will be conclusions. So let's get started with the idea of quantum sciences and with the talk. So here comes this word which was, I think, coined by John Preston, it will come also later, which is the idea of quantum supremacy, which is the idea of what can we do with a quantum system that we could not do with a classical one. And of course, one of the first answers which came out is let's do a quantum computer. And this is what I will try to explain in the next slides. So, the basics of every form of computation or of digital computation, there is the bit. So, which in classical terms, which I mean for our computer, like the laptop I'm using here, is a classical bit, which is basically a logical idea of a system which takes only 2 values. And for simplicity, I will dump these 2 values, 0 or 1. And so it can only be either 0 or 1. Then comes, I mean, the idea of making it quantum. And of course, I mean, here we will have the quantum bit, or the qubit if you want. And you also here have 2 states. One state, one quantum state. Imagine you have your hot atom there. It has many states. You take one state of the atom and you call it 0. And the other state of the atom, you call it 1. And here you have your qubit, basically. So in principle, a quantum bit is nothing particularly more complicated than a classical bit. It's just a quantum system which can take 2 values. And the point is that already here quantum mechanics sets in and makes it much more complicated because quantum mechanics, here it's technical maybe, but it's just a small remark, is a linear theory. And being it a linear theory, it can actually allow for superposition of actually the 2 states. And I mean, in more mathematical terms, maybe the good intuition is to think in terms of a vector space, a 2-dimensional vector space in which you have one state, which is the state called 0, and the other state, which is the state called 1. And then in this vector state, you can have basically a linear superposition of the 2 states, and this would be a perfectly allowed quantum state. In more physical terms, what I would say is the things are the polarization of the waves. So if you have your electromagnetic waves which propagates, you could have a transverse polarization, like electric field oscillation in this direction, or electric field oscillating in this direction. But there is no reason why you shouldn't make a superposition of the two, and for example, have electric field oscillating in another direction, or being circularly polarized. It's the same mathematics which is at the heart, and which makes basically the quantum bit a bit more rich than the classical bit, because the number of states which I can have in a two-level system is actually spanned by two angles, the angle theta and the angle phi. So, but this is just a bit technical, it's not really important. The point is that out of one quantum bit, I would like to construct a quantum resistor. So what I will do, I will take my system and I will repeat it, have many of them. And for example, if I can take 10 qubits, I will have many more possible states. So I could have all of them in the 0, or some of them in the 0, another in the 1, and so on and so forth. These are just some of the possibilities. And of course, because quantum mechanics is a linear kinetics, I could also have linear superpositions of these states, and so on and so forth, making it more and more general and more complicated. So what is then a quantum processor? A quantum processor is something which basically takes n qubits and just applies on these n qubits an operation. So this psi would be whatever, one of these, for example. And then I will apply an operation on this state. I will modify it, do something, and I will get another quantum state at the end. In the same way, there's in a sense, a quantum processor, a classical processor, which is in this computer, takes some currents in input and out comes other currents in outputs, which encode some information in there. And also here, like in a normal computer, we can have some logic gates. In particular, the most relevant ones are the gates which work on a single qubit, or the gates which work on 2 qubits. Okay, so the most important thing is that because quantum mechanics is linear and so on, I just have to specify what is the action of my gate on either the 0 or the 1 state and see what happens. For example, one possibility is that I could have a phase shift gate which leaves the 0 state untouched, or which takes the 1 state and applies a phase on front of it. This is an operation which I could do, for example, of my quantum state. Or another interesting one, which is very, very quantum in a sense, is the Hadamard gate, which takes the 0 state and out comes it the superposition of the 0 and 1. Or it takes the 1 state and out comes another superposition of the 0 and 1. If we think about the 2 qubits, I could imagine something a bit more exotic and more complicated, like for example a control knot. So now what I do, I take 2 qubits, and when the qubit on the left is 0, I don't do anything to the qubit on the right. And when the qubit on the left is 1, I actually change the qubit on the right, which is what is basically done here. So up to now, I would say, I mean, what I was trying to somehow to convince you is that if we really go to the bottom and we speak about this quantum computation, in a sense, at a formal point of view, it's somehow very similar to what one would do with a classical computer. Now, the interesting point comes now when one says, okay, having defined these rules of the game, which, okay, fine, are related to how quantum mechanics work. So can I really do now something which is actually more powerful than what I could do with a classical system? And the point is that, I mean, it was demonstrated in the 90s, but if you take this rule of the games, you can actually have what is called the super polynomial speed up of algorithms. So let's first mention these examples of super polynomial speed up. I think the most famous one, and the one which actually gave it a start to everything, is the idea of Shor's algorithm for finding the prime factors on natural number. This is a problem which in usual with our computers is usually tough, meaning that we don't know mathematically that it is tough, but we don't know algorithms for solving this problem easily, fast, in an efficient way. So if I give you a very big number with 10 digits and I ask you, so what are the prime factors of this number? Usually, the longer the number, the more exponential becomes the time it takes in order to find out these prime numbers. And what was demonstrated by Shor is that if you use a quantum computer and allow the rule of the game, which I said before, you could actually do that in much faster, let's say. And actually, more technically, the idea is that if I use a quantum computer, the time which takes to solve the problems is polynomially. Whereas if I do it with a classical computer, the time which takes to solve it is actually more than polynomial. For example, exponential with the length of the field. So which is basically what we were looking for. So this is really good news in a sense, because we found out, at least Shor found out, that using a quantum computer, it was actually possible to do things in a faster and more efficient and more powerful way. And okay, so somehow I should mention that actually examples of super polynomial speed up are actually kind of rare. So there are not many examples of algorithms which outperforms so drastically any classical computation. And I should also mention that, I mean, it is very natural to ask, so what is the source of this speed up? Why is the quantum computer much more faster? And still, after so many years, basically it's now 20 years after, we still don't know. So it's really highly debated. Some people say something, some people say other things. So just to give you an idea of how little still we know about this and how much there is still to do from a theoretical point of view. But having mentioned this problem of why a quantum system actually can do computations much faster than a classical one, I would like to mention one of the candidates somehow, which is under debate, so it's not certain, but still one of the candidates, is the concept of entanglement, which is something which is really typical of quantum systems and which does not appear in classical systems. So, as I was writing here, an entangled system is a quantum system, and it's composed of two parts, for example, of two atoms. And the point is that it cannot be fully described just by describing the properties of its constituents. So there are somehow correlations between the different constituents, which makes it impossible to understand everything of my system just by looking at the subpart. And really to contrast it with the idea of the classical case, so let's consider, for example, Newtonian mechanics of two balls, for example, like tennis balls, which are big balls and so on. If I want really to describe the cinematics of these systems, I mean, I just have to know where is the ball one and the ball and what is its velocity, and I need to know where is the second ball and its velocity. But as soon as I have all of these, I know everything about my system. So I can build up my knowledge of the full system just by looking first at the first ball and then at the second ball, and that's it. So if I do it for the quantum case, usually, I mean, we use the letter rho to describe the state of an atom, for example. It's not enough if I give you what is the state of the first atom and what is the state of the second atom. There are then several, there is really room of space, a lot of space for deciding what is actually the state of the global quantum system. And these new correlations, which cannot be understood in terms of Newtonian mechanics, are a good candidate, actually, for being what actually speeds up in our quantum algorithms. Then I think, I mean, you might be wondering now what is the experimental status of all of this. So I kind of try to give out what are the theoretical ideas at the base of these quantum sizes. What would like to know, so what have we done somehow in practice? Have we been able somehow to construct a quantum computer? And the answer is, at the moment, no, but we are trying to do it in a sense. And there are several experimental setups in which people is actually trying to construct a quantum computer. One of these is called trapped ions. So this is a trap. It's a big object which creates electric field which are able basically to stack some small ions inside this trap, and which can then be addressed with lasers and manipulated and so on and so forth. Another possibilities are optical lattices. So these are cold gases, these are neutral atoms, which can be actually very nicely trapped in this kind of lattice shape. And so the idea is also here somehow to put all of our atoms, which are really quantum, in these different minima of this strange potential, and then to, from outside, manipulate them using lasers or whatever light fields or magnetic fields. So bit more different is the idea of doing quantum computation using superconducting circuits. Here, one would like to use the currents, the superconducting currents of superconducting circuits as carrying information. So, for example, in this kind of circuits, currents flowing in one direction or in the other direction have different, can be associated to different qubit states. And the point is that also here, these currents, are really quantum objects. And the other idea is also, this was very, very powerful, especially at the beginning, the idea of doing nuclear magnetic resonance, which is the idea of actually doing computation using the spin states, the nuclear states of a big molecule, for example. So in general, the requirements for doing experiments using cold data, using quantum systems, is that one should have a system of which, basically, with a good approximation, I can extract two levels, which are somehow two states, which I can then manipulate with a good fidelity. So which I can initialize in whatever quantum state I want, which I can evolve in time with a good fidelity, which I can read out. And in particular, the other important thing is that I should also be able to put many of these qubits close together to let them interact and so on, because we want to go beyond single qubit computations. And the important thing, actually, which is what makes all of these particularly difficult, particularly challenging, is that we should have this system with low interaction with the environment. Because actually, the environment around these quantum systems is what actually spoils the quantum computation, is what actually destroys the quantum states which we have in our system. And right, so I wanted to say something more about this environment problem. And actually the question which is now raised by the people is, can we really realize and control the quantum system which is larger? So I don't want to do a single qubit, I want to have 10, I want to have hundreds, I want to have thousands of them. Yet, even though it is so large, it is profoundly quantum. So remember that the bigger I become, the more microscopic, and then classical mechanics starts to set in. So this is a really big problem. And the problem is that, interaction with an external environment causes decoherence. Decoherence is a technical term which is used in the field, which says basically that after a short time, my quantum object behaves like a classical object. Which is where then, I hit a wall, because in a sense, I cannot do anything anymore, at least in terms of my quantum speed up and things like that. So, the point is isolation from the environment is basically extremely important, but it's also what makes everything not easy. So for example, if you look at the experiments, at the real pictures in experiments where experiments with atomic gases are actually done, you see how complicated from a technical point of view these experiments are, although, we are now, it's a technology which is in development since the last 10, 20, 30 years. And for example, in order to limit the interaction with an environment, one has to use an ultra-cooled gases, which is levitated via magnetic forces, which then is put into a vacuum chamber, and which I then address from outside with laser light and so on. And the point is that at the end, after all of this cooling and manipulation, I can only have really control only over a few properties of this gas, which is basically what. So although I have still, a big vapor of ultra-cold quantum gases, I cannot control every single property of this gas, and which is basically what is still stopping us from really trying to perform real quantum computation using these systems. And just like a last slide, which gives an idea of how long is the path towards doing a quantum computation with these systems. So these are the two scientists, Serge Roche and David Weinlein, who won the Nobel Prize for Physics in 2012, which is a Nobel Prize very much related to these ideas of the quantum scientists. And if we read the Nobel motivation, is that for groundbreaking experimental methods that enable measuring and manipulating of individual quantum systems. So let's have a look at the timeline. Werner Heisenberg won the Nobel Prize in 1932 for the creation of quantum mechanics. And 80 years later, these two gentlemen won a Nobel Prize in physics for the manipulation of very small quantum systems. And now the new frontier, which we are actually challenging, limit is also challenging, is somehow really to try to control and manipulate complex big quantum systems, which would allow us in hopefully a not too far future really to do quantum computation or to really exploit the powerful of quantum mechanics. But meanwhile, I mean, people somehow got a bit, I wouldn't say skeptical, but I mean, interested in saying, okay, but while we try to get there, can we still understand something meanwhile? Can we still do something which is as exciting as quantum computation? So can we still do something which overcomes what we can do with classical systems? And the idea is, for example, to try to build a quantum simulator. So it's a simpler project, it's something which is a bit simpler, might be easier, and therefore might be actually realized in the closer future, but should still maybe show that it's possible to do something with quantum mechanics which we cannot do with classical mechanics. And in order to explain this idea of the quantum simulator, I thought about a couple of slides which are a little bit of a detour, which show how simulations can actually help us not only in the quantum world, but also in the classical world. So this is a church which was designed by Anton Gaudí in Barcelona, and this is somehow the draft which he pictured down. It's unfinished, unfortunately, and these are some of the pictures which one could show, one can take now. What has been done, it's the basement basically, and you see that the columns and all everything here is kind of rounded, and it has kind of a strange shape somehow, which is the point of the. I will come to that. The other thing which I wanted to show you is this very important pavilion, which was done by a very important architect, Otto Frey, in 1967 in Montreal for the World Exposition in Canada, in Montreal. And this is the German pavilion. And what I would like to show you is that you see these are very, I mean, it's characterized by this kind of tensile structures. No, it's like a tent which is held up by this big, I don't know what to call it. But anyway, it's something really, really big and so on. And the point which makes these two architectural examples similar, from my point of view, is that they were basically realized using small models, in a sense. So Gaudí was constructing this church basically using a small model of catenarias, which were called, which were coupled together in order to construct a structure which was one bending from top to bottom, basically only tensile, and which was then, once reverted, only compressing, which gave basically the best and most optimal shape for having the most solid structure. And this is also a study which was done by Otto Frey for computing actually these kind of shapes at that time. So this is a form-finding study model for Expo 67. But you see, I mean, this is a smaller model. So what makes these things kind of similar in a sense. So the equations which describe both how the pillars of the church are, of how this tensile structure should look like are known, because at the end they all boil down to Newtonian mechanics. It's something which is really well known. It's at the end is a force equal mass times acceleration at the end. But still, they could be very difficult to solve. I mean, it could be that in this configuration the equation becomes something intractable, either analytically or experimentally or whatever. So I don't solve the equations, but I build a small and controllable model, which is actually described by the same equation. Here comes the point, and which I can use in order to get information about the solution of the equation. So I don't want to make it too bold, but in a sense, what I'm doing here, I'm realizing a smaller model, which is described by the same equation, and by looking at the way this shape, this tensile structure takes shape, I know how this should look like when I make it bigger. When, apart from making it bigger 1 meter, I make it bigger as 100 meters, no? So rather than solving the equation, I just, in a sense, let nature compute for me. And the idea of the quantum simulator is basically the same. The idea is that let's do it quantum somehow. Let's find a quantum problem which I cannot solve, and let's find a smaller quantum system which I can use actually to solve those equations. And this is, I think, a very interesting idea. So first, we need a problem which we cannot solve. And here comes, it's one of the open questions of physics at the moment. It's the problem of high temperature superconductivity. So it earned a Nobel Prize to the two experimentalists which actually discovered it in 1986. It's an unconventional form of superconductivity which cannot be described with the typical equations of common superconductivity. So at the moment there are really no accepted theory explaining this phenomenon. The only thing which is kind of clear is that quantum mechanics, as usual in superconductivity, should really play a major role in understanding these systems. And well, people have been trying to solve this in several ways. For example, using computer simulation, or just sitting down at the table with paper and pen. Or, and this is the new idea somehow, let's try to solve this problem using a quantum simulator. So simulating with a quantum system these superconductors. And right, here comes the idea of the Hubbard model. So John Hubbard is a very important physicist of the 20th century. He was working on this stuff of the high temperature superconductivity, and he actually, after studying it and so on, I mean, he realized that, I mean, what could be probably the most important degrees of freedoms of this crystal, which actually bring them to be superconducting. And in terms of these simple degrees of freedom, he wrote down a model which is called the Hubbard model right now. So the Hubbard model yields an equation for the superconducting current of the system, which unfortunately at the moment nobody can solve. Of course, if I could solve that equation, I could then look at the result and benchmark it with the experiments and then see, okay, it's really the same, look, so I really have understood what is high temperature superconductivity. But if I cannot solve it, I cannot benchmark it, so I cannot be sure that I have solved it, that I have understood really what is at the basis of high temperature superconductivity. So the question is, can I find, for example, another quantum system, like for example, an ultra-cold atomic gas, which is also described by the Hubbard model? Because if yes, I could just look at it, look if also this system is superconducting, and try to compare the behavior of my small and controllable quantum system with the behavior of the superconductors, which I don't know how to explain. And this is basically what these people, and actually I should say also many other, just too prominent, but it's actually, I mean, something which many more people are working. These are Emanuel Bloch from the Max Planck Institute of Quantum Optics in Munich and Tilman Eslinger from the ETH in Zurich. With their research group, these people have prepared experiments where cold atomic gases are certainly described by the Hubbard model, so we know that. This is, and are investigating whether such gases actually behave like superconductors. So let's stress it. If the comparison between cold atoms and superconductors is consistent, we could say that we have verified that the Hubbard model describes also high temperature superconductors. But unfortunately, this requires the cold gases to be cooled to temperatures not yet achieved, which is a bit of the drawback. Okay? So we are still working, I mean, they are still working on that. But if one day they could be able somehow to cool down the cold gases to such low temperatures that where the Hubbard physics will really set in, they could be really able to see if there is some superconductivities in these gases and say, yes, look, it's really the Hubbard model which describes these superconductors. And of course, this is just one example of the many ideas which are around about doing really a quantum simulator, which is somehow the idea of using, let me repeat it, controllable complex quantum systems for understanding other quantum systems which we don't understand at the moment. So this is a bit of an intermediate summary which will conclude the first part of my talk, somehow the most broad audience, I would say. So the big goal on which this community is working on is really controlling and using complex quantum systems. One idea is that to do really brute force quantum computation, one quantum object which at the end can solve everything because it's like a computer, it's extremely multitasking. The other idea is to try to do quantum simulation, so a simpler quantum object for one specific task. That might be actually the key, somehow, the shift of paradigm, which maybe will enable us in reasonable times really to see that quantum objects can actually overcome what we can do using macroscopic classical objects. I would like to stress that still, again, I mean, always in this kind of research, the big problem is the coherence. Experimentalists have to work in really unfavorable conditions where everything becomes extremely difficult, and this is basically what is slowing us down. Although it's not clear if there is maybe some physical law which forbids us to get to that point. Anyway, so the big question which we would like to understand better is there already any evidence of superclassical behavior of quantum systems? And this is somehow the big open question which is triggering all of this work. So with this, I have concluded the most broad audience, most general part. I would like now to get a bit, to elaborate a bit more on like detailed topics somehow. It will get slightly more technical, but will stop me if it is becoming untractable or just useless. And the idea is basically the one of studying quantum memories and seeing how to store quantum information in these systems. So let's start from, again, quantum classical system, classical computers. I mean, arguably, I would say that memories are one of the most important devices in any system which does some computation. No? For example, in these computers, there are a lot of different ways of storing information which then will be processed later, or which should stay there while the computer is switched off, and then when you switch it on, it's there, or so on. So I think that, in a sense, how can you process information if you cannot remember it? So that's why I think quantum memories are one of the most important parts of a computer. And in a sense, you can also imagine memory as the most easy form of computation. You just apply the identity gate. You just don't do anything to the system, and you just leave it there. But so, how does it work? A classical memory, somehow, a memory which is inside this book, this notebook, for example. So, at the very simplest way, I mean, it's the most simple example which I can find. Of course, now if you really want to explain what happens in a laptop, you need much more sophisticated models. But at the lowest level, somehow, a memory, in a sense, is a ferromagnet, where you have different device domains, where all the magnetic moments of the atoms in the device domain are all aligned in one specific direction. And you take out two directions, for example, all of them up or all of them down, for example, and you encode information there. So you look, for example, in your hard disk driver, there are small parts in which all the magnetic moments are all aligned in some direction, and just by looking, measuring what is the alignment of these things, you just know if your memory is in the 0 or in the 1. And you can also manipulate just by applying a strong magnetic field. You can just switch them or read them and so on. So the point of this ferromagnet is that you have two configurations which have the same thermodynamic properties, which are not connected by local operations, because if I just act on one of these magnets, I just don't change all of them. Because if I just flip this magnet here, I mean, at the end, the big, I mean, if you just do a majority vote, you would conclude anyway that you are in the up state. And if you really want to switch from one to the other one, you really have to apply a global action of the system. So in a sense, this is an ideal system for a bit, and it protects the system from the so-called bit flip error, which is the error which flips the bit from 0 to 1, or so on. If we now try to go quantum and think in terms of quantum computers, we should now think of quantum memories, which again, I would argue, are one of the most fundamental ingredients for doing quantum computation. So we need a device which allows for some reliable storage of quantum states over long time. So remember, this is not easy because we have the coherence which sets in and changes our quantum states and makes the system from quantum a bit more classical in a sense. The point is that if you think in terms of quantum information, it turns out that there are actually even much more, I mean, in the sense, as the qubit has much more states with respect to the bit, it also is prone somehow to many more kind of errors. And apart from the bit flip, which I mentioned before, one of the other errors which you could have is the so-called error of dephasing. So let's see a bit what this is. You could take your atom and say, okay, my atom is my quantum memory, I can manipulate it. I just take two of the levels of my atoms, and I say one level is the 0 atom, the 0 state, and the other level is the 1 state. And then I initialize the system in a linear superposition, the one which I want, of the 0 and 1 state. So I come after some time, and if my states have changed a bit of energy, because, for example, there is a magnetic field which is there in the system, I will get basically a phase here in front, which is basically due to an energy difference of the state 0 and of the state 1, which is due to the presence of some external magnetic field. So this kind of phase which I get here in front scrambles my information, because the information is actually also in this kind of phases which appear here. And if I wait enough time, I mean, this will completely destroy, I mean, my information. And so it's really important for a quantum memory that the states 0 and 1 have the same energy even when I apply perturbation. Because this phase which I'm getting here is only due to the fact that my magnetic field is just changing the energy of these states. So we need models somehow which not only have the properties of a classical magnet, which makes it robust against bit flip, but I also need models which have the property that when I arrive with a perturbation, like a magnetic field, I don't get an energy difference between the two states. And here comes, I think, one of the most brilliant and interesting ideas of the last decades, which is the idea of Alexei Kitaev of using systems with topological order for doing this. He basically realized that there are models which have the following properties. On one hand, they have, I mean, these are many body models. In a sense, are like in our ferromagnet, I have many spins, many magnets in the system. Here, I also have many spins or many small constituents in the system. And I mean, he realized that these models, like a system with topological order, I could have states with the same thermodynamic properties, which are not connected by local operation, and which can be changed one to the other one only with the action of a global operation over all of the system, which makes the system somehow protected against bit flip. But the point where he also got is that if I apply a perturbation to my system, like a small magnetic field in the case of before, I don't have a different energy for these states. So they shift in energy in the same way, so that at the end they don't dephase because they don't get any energy difference. And this is really not trivial and not easy to achieve, but somehow this is the idea of Alexei Kitaev, and it was very, very interesting. The problem is that, again, this does not close the story, because I mean, when Kitaev was popularizing this idea and writing in papers and so on, people start to say, wow, topological model implies great memory because it protects me against any kind of perturbation. But again, bad news, it was a bit of a shock when these people, Alitzky, Fannes, and Horodecki, found out that also in the case of topological models, you can have bad perturbation. So the situation is still much more rich, much more complicated than we would have hoped for. And for example, here in this kind of systems, which Kitaev was proposing as good quantum memories, the problem of a thermal environment which will thermalize our information is actually the killing one, which will destroy any kind of, will also induce the coherence in this kind of models. So, well, this is maybe a bit of a technical point, but I will get a bit technical now. So I would like to have a memory in these systems where the storage time of my memory increases with the size of the system, because I really want all of the small constituents which compose my memory to collaborate actively in order to really protect the information in my system. And I mean, the point of the demonstration of these gentlemen is that if you have thermal noise in your system, I mean, there is the storage time of your system is actually not after, I mean, it increases when you make it bigger, but sometimes it stops increasing. And even if you make it 100 times bigger, you don't get any factor in relaxation time of the memory, which basically means that the many-body system is not collaborating as a whole for the protection of the qubit. And this is a bit of the news. So in a sense, just summarizing this idea, We have one side, the atomic quantum memory, where I have a single atom, which is easy to manipulate because it's a single atom, but is in a sense unreliable because whatever perturbation will just scramble my information. And on the other hand, I have this kind of deep topological quantum memories, which are kind of difficult to manipulate, but maybe more reliable, although there should be a question mark here. And also, I should also mention that whereas manipulation of atomic systems has been already proved, we still are looking, we are still trying somehow to find the systems which display this kind of topological order, which is expected to play a major role in the construction of quantum memory and so on. And right, so here concerning the reliability, as I said, all the benchmark quantities of the topological quantum memory should improve when the size of the system increases, and which in a sense means that the intricacies of an n-particle state are paid back by an intrinsic stability, or if you want, that n particles are collaborating to protect the information, or if you want more physics-like, we don't have experiments, so let's at least look at scaling, so that if I have found this and the experimentalist comes and say, oh, I have built a system which is small and has a memory time of 1 second, I can tell him just make it twice as large and you will get a memory time which is much longer. And what we have been doing in Munich, in Pisa, with people, with collaborators, was basically to try somehow to put a bit of quantum information quantities and try to do a bit of a detailed quantum information analysis of how the information is stored in these systems and how much information can I really hope to store in this system, how much information I really hope to retrieve easily or in a difficult way out of my topological system. And this brings basically me to the last part of the talk, which I will try to sketch in a very fast way. And as it comes to kind of original results, I should really acknowledge that the many people with whom this work has been done, because it's really not only my work, so Ignacio Sirac, my PhD advisor in Munich, Matteo Ritz, Michel Lukin, and Matteo Politi, David Rossin, with whom I'm mainly working now, Peter Giovannetti and Rosario Fax, and a bit of funding from different European and Italian and German sources. So let's try to face this kind of technical slide. So what are we doing then when we consider a topological quantum memory? We have a general qubit. We write it down basically in a big topological system of size n. We leave there our topological system after some time. Here this part means just that some noise will act in my system. I then come after some time t. I look at my system and I try with a recovery operation to take out a qubit out of that. If my information is still there because I was exploiting the good properties of a topological system, there should be a recovery operation which, once it acts on the topological system, it takes out the information and reconstructs a qubit which is basically similar to the initial one. So the question we have been addressing is, so given a decoherence channel, which means given a noise model, let's call it a noise model, which is the best recovery operation which I can apply? Because maybe, what usually happens is that you just apply a recovery operation which you can do, but you are not usually considering what is the best one to recover the information. And also, how does the memory side and the memory time associated to the best recovery operation depends on the size n. Again, I want to see really n particles collaborating to the protection of my qubit. And what we have been basically working on is topological models characterized by the presence of Majorana fermions. Hector Majorana is an Italian physicist who disappeared abruptly in 1938, still living very young, but still leaving a lot of very important contributions to physics. And so we have considered basically some specific kind of noise models. It turned out that addressing the most general case is really a bit too difficult for the moment. But for these models, we have been able to characterize the information which is still present in the memory after the noise action. And within this very large group of noise models, we have actually been doing some specific computations for some specific noise models. And among the most interesting results which we have found, I would like to mention the fact that in these systems, for example, if I have particles leaking in or out of my quantum memory, this basically is going to destroy without hope the information which I have in the system. But the good, interesting thing was that there were cases in which some noise models were expected basically to destroy the information in the system. And we found out that actually the information was still in the system, but these people were just considering, in a sense, a recovery operation which was physically motivated, but not mathematically the best one to extract the information. So, and if one used the best recovery operation, actually it was possible to show that the information was still there to be used. So in a sense, I mean, there was something to discover, I would say. And I would also say that now we are trying to be a bit more careful also with the problem of the complexity of the recovery operation. As I said to you before, manipulating a complex quantum system is tough. We should not somehow give prescription of doing physical actions which at the end we cannot do experimentally. And right now, even a bit more technical, somehow we are now considering also trying to be a bit more precise also in the way the noise model is inserted in the problem of the topological memories, because I mean, people working in quantum mechanics know that there are two ways of including a noise model. Either you take your system and then you say, okay, and then the environment will do this, and you write it by hand. Or you first consider all of the physics of the system plus environment, and then you discard the effect of the environment. So the second approach, of course, is much more difficult because at the beginning it requires you to consider all of the effect of the environment, but it's also what gives the most interesting, I think, more reliable results. So what we are doing now, we are really solving some kind of specific system environment dynamics, understanding why some noise models spoil the information and some other ones do not. So we are really trying to go down to the problem of these topological quantum memories and trying to understand why in some cases the information is still there and why in some other cases a noise model destroys the information. And this requires some technical difficulties, so which I don't want to speak about anymore. So with this, I'm really done, and which really brings me to the conclusions of this talk. So let's have again a look at the big introductory questions. So this is John Preskill. He gave a very interesting lecture in 2011 about quantum computing and entanglement frontier, and he was really pointing out this big problem in his seminal talk, I would say. So can we really control a complex quantum system? And if we can, so what? So again, physicists are really still turning around this apparently tough but still exciting and interesting question. And again, so it's a really a difficult way somehow which I have taken this picture because it's really, not only is long, but it's also kind of full of complicated issues to solve. So what we are really trying to understand is whether a quantum system is more powerful than a classical computer. Is this really true? Can we really make it sure beyond any mathematical doubt? In a sense, can we really realize big and microscopic quantum systems for doing all of these things? Because still, I mean, it's kind of difficult. And also important question, is this something we can hope to do in some decades? Or hundreds of years? Or who knows? But apart from this, I hope to have stressed enough that we should not only look at the long-term goal, but it's such an exciting research field where also the intermediate goals are really exciting and motivating a lot of physics. So even if, I would like to make this point maybe a bit provocative, even if we never will get to build up a fully fledged quantum computer, I would say that it was really worth endeavoring into this field because it's actually letting us better understand a lot of properties of nature at the atomic scale. And it's actually leading to a flourishing of theoretical ideas, experimental ideas. And I think it's a really pleasure somehow to work in this topic. And with this, I'd like to thank you for your patience for this very long talk, and I would be happy to answer some questions. Thank you.
Time for a couple of questions. Anybody wants to? Yeah.
I have two questions. First of all, they description of the qubit, we say that we can have the linear superpositions of the two quantum states of the atom. How many such states can we have?
In a superposition? In principle, as many as you want. As many as you want. I mean, of course, so from in a sense, what you are asking, I would say it's mathematically not really well defined because it's in a sense, I mean, you have one quantum, I mean, you could imagine your state to be in a superposition of already as many as you want other quantum states. Just play a bit with mathematics. But to make it a bit more precise, if you consider the energy eigenstates of your system, you can make it in a linear superposition of some of them. Of course, I mean, having different energy will require you a bit more complicated things, and also it will involve, I mean, during the time evolution, a bit of dephasing. But in principle, I mean, there is no physical constraint on the number of states which you can make in linear superposition.
So how much information can we store?
I mean, if you use a qubit, it's still the qubit. I mean, if you use a qubit, so if you start saying, okay, I just consider two states, then the information you can do is one qubit. But what I was trying to argue is that if you take many qubits, then of course, I mean, it's scale actually the number of states which you have at your disposal scales exponentially with the number of atoms.
So let's say we want to transfer information from a classical to a quantum computer. In a classical computer, we can either store 0 or 1. Is it the same for the quantum computer or for the qubit? Or can we store several bits in a qubit?
No, I would say that you... okay, so I'm not really an expert about this, but in principle I would say that you would just go for transposition. But the point is that also the algorithms which you want to run with a quantum computer are in concept really different from the algorithms which you want to. But in a sense, I would do that. There should be a one-to-one correspondence. I would say that.
And the second question is about the topological
order
model. Yes, this toroidal form we saw. Is it several atoms in such a shape?
Right. So the way to think at it is a bit, say, it's a bit like this, I would say. Well, I draw just a rectangular, but I imagine it as filled with many atoms with magnetic moments, and there I was imagining something like this. But also you shouldn't take too seriously this toroidal shape.
Okay,
you could
so
also
there can be many.
You could, yeah, yes, exactly. Actually, the shape is one of the important quantities in this topic of the topological order, but anyway, you could imagine also to have a system just simply rectangular two-dimensional systems with magnetic moments.
Any other questions, comments? I have a quick comment/question. The last few months, or maybe a couple of years now, there's interest of a few companies like Google and D-Wave and several private institutions in quantum computing. So you might have heard about Google bought, so they set up their own.
Yes, I mean,
so maybe you want to comment on those efforts and what do you think?
So, I mean, I should also say that I am not an expert on what they are doing, but to my impression, I was actually attending a seminar by people working on this. Okay, maybe we restate that. I mean, there is a company, especially it's a Canadian company, it's called D-Wave, which is basically starting to sell quantum computers. So while the scientific community working in universities is still trying to answer the big question mark, which I tried to pose here in this seminar, they said, okay, we have actually a quantum computer, you are just too big, and we are starting to sell them. And we are making a lot of money out of that because we are selling it to the United States Army, I think, or some other. So I would say that, how is the scientific community reacting to that? I would say that we are starting now to publish more and more data about their things. So this is, it's becoming more and more clear how their devices are done. And there is for sure something interesting in that. They are based on this idea of the superconducting circuits. I'm sure there is a lot of things to learn there. But still, if you really go down and try to nail it down to the question, is it working? And you try to do benchmark about what it's not working. So, they just have found a way of squeezing money out of a lot of companies. That's the impression. Although I think the scientific part, it's probably worth a look.
Yes. What are they solving? It's actually closer to what engineers call annealing. And when you have, let's say, some sort of function has lots of minima, you want to find the global minimum, so they have this kind of algorithms. There's a quantum annealing, and that kind of works a little bit easier compared to factoring algorithm or something else. So there are some setups with superconducting circuits that you can do those things. So that part is quantum in a sense, but it's not fully quantum computing. But you might read it in the news that there's a quantum computer already out. It is not a full quantum computer, but certain
surely there is something interesting.
Certain properties of it are interesting. Yeah.
What annealing means?
Annealing. Okay, so this is there is this classical annealing, this is the quantum annealing. So, in a sense, imagine you have a function, as I said, that you have a lot of. It's a global optimization problem of some sort. In the simple version, is you have a function that has a lot of minima, and there's some sort of algorithm you want to find the global minimum. So there is a mechanical way or a physical way to approach that. Imagine you have a ball that you throw in this potential, it will go and sit on the minimum, and this is the solution. And this is the mathematical approach for that as well. So this device does this quantum physical ball searching point without having to do an algorithm. It does it faster than you would do it in any computational way, roughly.
This computer that D-wave cells, does it have any difference compared to a classical computer?
This is a big question, so maybe you can comment on that.
Some people have tried to. So, the D-wave computer also comes a bit with the idea of the quantum simulator. The D-wave computer can only solve one specific problem. It's not completely fully fledged. But what, of course, they can say is that without computational effort, you can map a lot of classical tough problems into that one. So, but anyway, let's first fix the fact that it can only solve one particular problem. So then I say, okay, let's write down the program. Let's take the best classical computer which we have, and let's take the wave computer, and let's give them lots of these different problems and see which one is better. And basically, it turns out that there is a correlation between the problems which you can solve reliably with the D-wave and the problems which we can solve reliably with our classical computers. The point is that at the moment, D-wave is still so small that we can basically compute with our computers the same problems. If it will become faster, it could be actually able to overcome this benchmarking test in a sense. But at the moment, we can benchmark it with reliability, and it's not better than whatever algorithm doing annealing which we have without any quantum.
But if there is something quantum there, the difference will be proved if the wave can go bigger. I think they have 500 or qubits now, 512 or 1024 or something like that.
So it's in California, it's kind of becoming really a hot topic, and also in the United States in general, I think. Because in a sense, they are selling it very well. And
there are people from the academia involved in this, in the evaluating of the machine, because usually companies give you a black box initially. They don't say what is inside. Now they kind of opening the box, and they have invited some academics, some colleagues of us and collaborators to say what they think. And there is also some, normal computational people trying to run those algorithms. Some people, like from ETH, there's the group, Troya there, and so on. But asking the same question to the classical computer and the quantum computer is also a difficult task because they speak a different language. So you cannot compare the solutions, the answers, if the questions are not exactly the same. So you have to be really sure that you're asking the same question and evaluating you're asking the same question in a proper way.
The first one is it possible to prevent the decoherence in a quantum system, theoretically or practically?
Right. So this is what at least, okay. Is it possible to prevent it? Well, that's what we are trying to do in a sense. So, for example, if I isolate even better my systems from the environment, I mean, given that what is making my system decohere is the fact that it has an environment around it with which it exchanges information, excitations, energies, and so on. If I make it as decoupled as possible from the environment, I'm sure to be able somehow to diminish the coherence in the system. But here comes also a bit of the tricky part, because if you want to manipulate it, so you are coming and touching it and doing something to it, so you usually also destroy it a bit, at least the information part of it. So, but in a sense, I would say yes, it is possible to do it. So it's only very, very difficult, I would say.
Okay, so if there are no more questions, let's start.
There
is one. Sorry, didn't see.
You said before that D-Wave's computer, you said about 500 qubits that can manage the...
They have 512 qubits, I think, on D-Wave 1, and now they are at, the new machine is maybe 1,000.
And how do we compare the speed of these two computers?
Yeah, this is what I said about the question, because all the notions of clock speed and processor power, they're very different here. I mean, here, the speaker didn't have time to go through the steps. I mean, you have to initialize your quantum computer in some initial state, and then you have to do your quantum operations and do your quantum algorithm, and then you do your measurements. These are slightly different concepts that how the normal computer works. So the concept of time and speed, one has to be careful how to define and how to compare. So that's why this is open still, whether what they do can or cannot be done with a big cluster or a supercomputer, for example.
Okay.
But the scaling, because of the quantum language, at least mathematically, in theory, if you have a machine that can run Shor's algorithm, which is exponential, even with 100 qubits, you're already faster than anything that could be ever built in by plugging all the computers of the Earth together because of the exponential thing. But the moment the challenge is technical, is not mathematical. Mathematically, quantum computing is faster, but to build it is.
Yes, it's really the engineering and building problem at the moment. The theory, I mean, the fact that Shor algorithms achieve the speed up with respect to a classical computer is given at the moment. Yes. So the point now is to do it.
It's just that experimentally we have managed to implement Shor's algorithm only in very small systems because of the coherence. 5, 10, maybe 20 qubits, 30 qubits. And then for 30 qubits, I mean, a big cluster can already do the same thing. But if you go to 100 qubits, it's a huge difference. I mean, you cannot catch it with a massive computer.
So, for example, I think just coming back to this, if you look at these, for example, these are the cold ions. I think at the moment in these setups we have perfect control over 8 qubits.
Yes.
So, and this was achieved, I would say, in 10, 12 years of work, starting from 1 to 8. And for the nuclear magnetic resonance, I think they tried to implement the Shor algorithms over 7 qubits at some point, no? And they were able to factor 15.
Okay.
So they found out that 15 is 5 times 3. Okay, so
yeah, superconducting qubits are kind of coming up very, very strongly these days.
Yes.
And
now they're becoming the
and actually the D-Wave machine is built on superconducting circuits. You take a circuit, a normal circuit, we have a computer, but you have superconducting wires, you cool them down in a massive fridge. This is a fridge basically, and when it reaches the superconducting temperature, the current just goes around freely without any resistance, And because these are very tiny circuits, they are quantized. And you can do your quantum gates and quantum operations there. And this is kind of one of the most promising technologies out of this
Yes.
4 or 5 at the moment, which are all competing for the same thing.
Of course, it would be great to have many quantum computers built on in different systems, because then you could have a lot of possibilities for benchmarking and so on. Really open-minded here.
Yeah. Okay. All right, so if there are no more questions, let's thank Leonardo again.
Thank you.